All right, howdy guys. Let me get this SWAT set up just 1 second. All right. Okay, I'm hoping you guys can see this. So here we are. My name is Jackson Rizzolo. It's nice to meet y'all, even though I'm not really meeting you. And right here, I'm here to talk you through some acid-base titration reactions. Whoop-de-doo, isn't it? All right, let's get this over with. Now, our problem statement. We have 0.5 molar sodium hydroxide is going to be added to a 100 milliliter solution of 0.2 molar acetic acid. Acetic acid is going to be a weak acid. Sodium hydroxide is a strong base, as satisfying our requirements. And as you see, 0.5 molar, 0.2 molar, 100 milliliters, those will be relevant later. Now, for our initial pH, we don't really need any sodium hydroxide because it's just going to be our plain old acetic acid. That's all it's going to be in there. So first off, we have our reaction. It's just acetic acid and water. It breaks down. We get this right here. This is what we're after, H3O plus. So as we know from our reaction, or as we know from our problem statement, our acetic acid is 0.2 molar. So we plug that in here. We have our ice. We don't care about water. This is all zeros, minus X plus X. And here we have this and this. So we get all this. We finish our ice table. And then we go down here, our K is going to be 1.8 times 10 to the negative fifth. We assume that. And so up here, A is going to be relating to this right here. And HA is going to be considering our acetic acid, which we don't really account for the X because it falls under the threshold. We end up with just 1.8 times 10 to the negative fifth equaling X squared over 0.2. which X equals 0.01897. Then we throw that into our pH. We take the negative log of it, which sends us with solution with a pH of 0.271, which makes sense considering this is just straight up acetic acid, regular acid, no base added to it, of a fairly good strength too. So looks good. Now we're going to go straight to our equivalence reaction. So right now we know our acetic acid is 0.2 molar. We have 0.1 liters of it. So we take that, multiply them together, and we end up with 0.02 moles. So now we go over to our sodium hydroxide. We know we have it. So we know it's 0.5 molar. We know we need 0.2 moles of it because this is an equivalence reaction, which means we need to have the same number of moles. So we take that, we divide our 0.5 on our 0.2. 0.02, and we therefore 0.04 liters or 400 milliliters, 40 milliliters, my bad. Then we go and we write out our reaction. Sodium hydroxide plus acetic acid breaks down into, well, I can't remember the name, but that plus water. So we go in with our ice table. We get all this. This should all equal out to zero because it's an equivalence reaction. There should be nothing left except for this. So now we take that 0.02 mole, then we add our 0.02 or 0.1 liters and our 0.4 liters. We get 14 liters. We divide the two of them and we get 0.14 molar of what it breaks down into. Now we're going on to our next slide, which is our equivalence reaction continued. So we have ourselves a fancy schmancy chemical formula, which is basically taking the products from last time and we're breaking them down even further. So we go in our equivalence reaction, we're stuck with the 0.04 negative X and 0.14 minus X. And same over here, we don't put water. Now we plug this in to find our KB. Let's see, BH is going to be this over here, which is pretty self-explanatory, and B is was our product in our last ice table. So now we can find our KB by using our KW and KA, which we know from earlier. KW is just a constant, and we know our KA from, I think it was our initial reactions. So then that has to equal X, which equals 5.6 times 10 to the negative 10, which then that has to equal over here. These have to equal, which is X squared over 0.143. So this falls under 5%, so we don't really count it, but it's still there just for now. Yeah, it's good bookkeeping, I reckon. So we get an X of So that x equals 2.16 times 10 to the negative fifth, which then we can plug it in over here to find our P of OH. So we plug it out, we get a negative log of that. That equals 4.6. And now to find our pH, it equals, that should be an equal sign right there, my bad. It was 14 minus 4.666 repeating, which ends up with a pH of 9.334. That's our equivalence when equal. All right. Now, going to after equivalence. So we know for equivalence, going back a little bit, we only need 0.4 liters of NaOH, sodium hydroxide. Now, after equivalence, we're going to add 100 milliliters, so 0.1 liter, which should be just a little bit over double the amount. So this should be well after equivalence. So we know our sodium hydroxide is 0.5 molar. We're taking 0.1 liters of it. So that's 0.05 molar. Now, we take our acetic acid. We only have 0.1 liters of it, and it's 0.2 molar. So once again, we have 0.02 moles. We have 0.05 moles over here. We have our ice table. Then once again, we just fill it out. We're left, acetic acid should zero out because we should use up all of it and still have some sodium hydroxide left over, which we do. So then we go and we plug in, we find, we add up our amounts. We had a liter here and we had a liter here, which is 2 liters. And we divide that, or no, we divide our remaining moles of sodium hydroxide by how many liters we have, get our molarity. Then we go and we have another chemical reaction. We take our sodium hydroxide and we break it down to its base components, sodium hydroxide. So that should break down. This is an account. So we have our POH equals negative log of 0.015, which equals 1.823. Then go and find our pH once again. We take 14, we subtract it from, we subtract 14, subtract 1.823 from 14. We end up with a pH after equivalence of 12.176, which once again makes sense because we are adding a whole lot of base in there. Like I said, just daggone, it's near what, double, 2.25 of how much there needs to get equivalent reaction. So it makes sense. It makes sense. Now, we're going to go over some real world applications, stuff like this. So I'm a geology / geotech studies major. So what that means is I go out and I get to play in the dirt and look at rocks all day. So an important part of that is we're going to take a lot of soil samples, a lot of water samples, and a big part of our job is to go in there, and if someone asks for soil analysis, to look and see, hey, we're planning to build something here. It could be a road, it could be residential. We want to look at the soil and we want to see what we can build on there. And we want to see if there are any underlying hazards in the area. So one of the big ways we need to do that is we're going to take the pH of the soil. That can help indicate any sort of toxins in the area. It can indicate whether the area can be zoned as residential or commercial. It means, say, farmland is a big one. It's like, say you have a guy who's coming in like, hey, I bought this plot of farmland and nothing's growing there. What's going on? Oh, hey, let me take the pH of the area, see what's up. Oh, yeah, your soil's acidic. You need to go, put some baking soda in there, something. We have runoff and damage analysis. Say there's, a big oil spill or a gas station or something, big like factory down the way leaks or has some contamination that seeps into the ground. You can use the pH samples of soil to figure out how far it's spread, and use that to figure out how far it's going to spread over a period of time. And all just that sort of stuff. It's pH samples are what we use for it. And here are my sources. This is basically this one guy on YouTube helped me out a whole bunch, and that was about it. All right. Well, hope you guys had as fun as me. So, and